full house again with, in terms of speakers. So just a wee word to the speakers. I will be waving the threatening cards as we go along. Very first conference I ever spoke, the chairman threw potatoes at people that went over time, but I don't have any with me, so we'll just have to put up the cards. The first speaker is David Woolf, and David, do you want to take the podium?
Okay, I'm actually not going to talk an awful lot about modelling. I'm going to sort of talk about some implications of modelling, really, particularly looking at how the tidal resource at different sites interacts. Some of the work is sort of my own quite recently, but it also feeds from work that Matthew Easton did at UHI when he was my PhD student. So he's on here as well. So this is basically the structure of the talk. We're going to provide some sort of motivation for why you want to know how tidal resources interact with each other, both in terms of if you're Mr. Energy hungry, how you get the most energy out, and also as Mr. Environmentally concerned, trying to understand what the environmental effects might be. I'm going to describe a couple of different modelling approaches, one of which is very much common fare. The other is nowadays a little bit unusual. It's sort of a very simple approach people used to use when we didn't have quite such powerful computers, but it's also something we've gone back to recently because it helps to interpret the more and more complicated models as much as anything else, and you can also run an awful lot of models very quickly. I'm going to sort of do a slightly non-standard description of interactions rather than normal near-field, far-field. I'm going to describe something slightly different, which seems appropriate for sets of channels. And I'm going to move on to conclusions, which will include some sort of thinking about the policy and governance implications. So first on to this motivation section. And the importance why, if we take it as given that there is some sort of interaction, why that's important, again, from an energy hungry point of view, it means we can't just model each site separately and add them all up and we know what the energy is. Equally, it's not obvious how you should exploit the resource, because you realise that if you, in the process of exploiting one resource, you change another. So how do you optimise getting the best total? And that partly leads on to the idea of having models which allows you to do a lot of experimentation. But there's also some simple principles you can get to quite quickly. The most basic of which is summarised in sort of it's in inverted commas there, the idea that parallel developments tend to be good, ones in series tend to be bad. And then going on to the environmental effects, I think when people started first talking about environmental, particularly ecological effects of tidal renewable development, they tended to think about things which were quite local, displacements, collision, where if you knew things coincided, and to use Ian Davies' phrase for a GIS system, you could pile things on top of each other, and if you know if they geographically coincide, then there's a potential for interaction. If you have things that act as a difference, which is what we're talking about here with the tidal interactions, things become a lot more difficult to deal with in terms of finding the potential interactions, identifying the potential interactions. It's not the only, for instance, migration also will give you this difficulty, but a lot of that sort of thing follows from understanding how the flow and fluid dynamics behaves. Okay, to move on to the modelling approaches, I can even note those who are not into the physical models probably will recognise some of the features of this. Basically, this is sort of an old traditional type of model, which is a structured grid. So basically, the part of the world divided into squares in this case, or rectangles in this case. And in this case, you have a fine resolution grid for the area you're really interested in, and a slightly less high resolution for outside. There's a lot of rectangles there, and that's rather typical. One reason why there has to be a lot of rectangles is because if you're going to talk about changing something in the middle there, what you would normally like to do is assume that nothing's changing at the boundary, and in order to do that you have to take the boundary a very long way away, and that makes the whole computational process very slow. So something you can do which is an awful lot simpler is the idea of basically using an electrical circuit analog. And it's particularly useful, for instance, if you have, this is Pentland Firth in Orkney, you have a system of channels and harbours. You can do something that looks a bit comical, but it does help to understand what will go on, which is basically to add and represent all of that as an electrical circuit. So typically a short channel can just be represented by a resistance or an inductance. I'm going to simplify that further in this talk, just for the simplify explaining things, which is just to represent most channels as a simple resistance, which we can change. So if you're interested in that method, I've published something recently, and that's the citation. Okay, so we're going to move on to talking about different types of interactions. Let's actually put the bold wrong. First of all, I'm going to talk about the systemic and the inter-channel effects, and then move on to the intra-channel effects in a minute. And I have to say, this next bit is not my own work, apart from borrowing things from two papers by Scott Draper and colleagues, who looked at, in a very simplified way, looking at how much energy you could extract from Pentland Firth, and they looked at different possibilities. A is something across the entire main channel, B, C and D across the entire channel but in 3 bits divided by the 2 islands, and E it only partially crosses the channel near the northeastern end. Extracted a very few results from that paper, and I encourage you to read those papers, particularly looking at what happens at B if you either develop that on its own or you develop it in tandem with one or more of the others. And turns out the results are rather remarkably dramatic, I think. I should say that they're particularly dramatic because what's calculated here is the absolute maximum you could possibly extract from B, depending on what you're doing. So in each case, we're looking at the energy from site B alone, but we're in the first case, that's the only one that's developed. In the other cases, one or more of the other sites are developed. So on its own, you get about 122 megawatts. But if you also develop the middle channel, you almost double that. And if you develop the middle channel and the channel to the north, so you basically enclose the entire channel, you get something like 160% more in channel B than you would if you only developed channel B. So I think that sort of demonstrates in this simple example that how dramatic the effect can be. You've got an extraordinarily large effect on the maximum possible energy you can get out of any one channel. The other one, if I just flip back, and E looks like it probably has absolutely nothing to do with B, because if you think about flow through B, it will go nowhere near E. But nevertheless, if you look at the calculations for that one, what you find is that if you also develop E alongside B, then that significantly reduces the energy you get out of B. So there's a conflict. So basically this substantiates the idea that developments in parallel across a channel help each other, those in series hurt each other. So this is the most simple possible model you could make of that, and it helps to explain what's going on, is that you basically have a circuit diagram where you represent 2 channels, one of which you're going to develop and one of which you're going to leave alone. So I call one the main channel, one the bypass channel, and within the main channel I'm going to add this load resistance RL, which I can crank up and crank up. And if you do that, you can immediately understand not only how you will affect the currents in the main channel, but also in the bypass channel and in the exterior area. So this basically separates two ideas, one of which is a so-called inter-channel effect. What do I do to the neighbouring channel? And the systemic effect is what I do to the rest of the world. Okay, so that's all been done and dusted. What I was interested in, just looking at Matthew's results from his modelling, is the extent to which that will also work if you just, rather than have two clearly separated channels which are separated by an island or other landmass, is if you just take a single channel and cut its lengthways. And so this is the example, this is basically the geographical domain of Matthew's model, and this is what he looked at. So he has a wide domain, which is pretty much similar to the one we saw earlier, of much of the north of Scotland, and a narrow domain that focuses on the inner sound of Stroma, which is basically Site B, which we've already talked about. And in this case, he took, rather than the theoretical case where you have a tidal array that fills entirely the width of the channel, you have a more plausible practical development of the channel where you have rows of tidal turbines in the deep water and you leave the shallower water alone, which is certainly more practical. And this does only leave the shallow water empty. But what you see if you run the model, what this shows is the change relative to without the tidal array. And what you find is basically that the current is reduced where the array is and along that line, but generally increased outside of it. And so there is detail there, obviously, that you can't possibly capture in a simple model. But there's a very simple general effect which we can capture by this. And if you're a rake, you will notice this is basically the same slide I've already shown. The only thing I've done is change the title and the labelling on the right. So in this case, you're just representing the single channel which I've split lengthways by the bit in the oval there, and then everything else by the external circuit. And this, again, seems to do a reasonable job, at least as an explanatory model to describe what's going on. Right. The importance of this is if you do have this leakage, if you compare what happens if you do a full width development and a partial width development, that sort of graphically shows the change. And what you find is actually you change things generally more if you only have a partial width. So you have to be aware of doing a partial width change. Right. Move on very quickly and move on to thinking about what this does if somebody's deciding what proposals to allow through. So I have this very simple cartoon land. Make it not parochial, it's not Scotland or it's not Caithness and Orkney, it's just anywhere. And I contrive bits of this two islands because it just happens to make a nice case if you make it two islands. And have, through jurisdiction A, we have two proposals, A1 and A2, and jurisdiction B, we have B1 and B2. And we represent that again by a nice simple circuit. And then we ask ourselves a question, okay, suppose one of those developments is given the green light, so there's a yes for that, a no for the rest. Well, how good is that going to be? And you could say, well, that could be a bad strategy, questionable strategy, good strategy. Well, I say that's a questionable strategy because it might work, but the trouble is a lot of the energy will leak through the rest of the circuit. That's fine. This one, for reasons best known to himself, one of the jurisdictions gives a green light to both, and the other jurisdiction says no to both. And this is clearly bad, and both jurisdictions should realise this. So that's a bad strategy. This one's more interesting because this is what possibly happens if the jurisdictions don't talk to each other enough. Because they both allow one, which is perfectly sensible, but because they choose ones diagonal to each other in a sense, what will happen is most of the flow will go through, zigzag through, avoiding both of those developments, essentially. And so that is definitely bad, and it's come about because they haven't talked to each other. So good is something like that. But they talk to each other, and they both allowed one through, and they're such that you've wholly blocked the channel at one of the two places. And it doesn't really matter which you choose. So just to finish just a few things, I talked about different modelling approaches. This is a very well-known approach, which all modellers should repeat to themselves often, that essentially all models are wrong, but some are useful. What I would contend is this very simple electrical circuit approach is useful, partly because it allows you to explain things, partly because it allows you to experiment a lot. And we do need to think about what different sets of models we use and have a sensible diversity of model, but not duplicate ourselves. The next set of conclusions are understanding action in the distance. And two things we should not confuse is we shouldn't confuse something being undeveloped with being unaltered. I mean, you could also make that same thing in relation to climate change, for instance, but the simple fact that we're not actually going in and doing anything doesn't mean it's not going to change. And sometimes, and following from that, you may have to be active in order to conserve what you want to conserve. And final thing relating to that last thing is that you do have to have systems and policies that enable strategic decisions. So you don't have this disconnect where people make sensible decisions on their own, but when you look at it in total, it makes no sense whatsoever. Thank you very much.
Unfortunately, with a full programme, I think the questions will have to be over the coffee break. Next speaker is Ian Ashton. Ian, you can take your place. Just start when ready.